I've been working in the military for 6 years. I like structure. I like being in control of things. A complex system is hard to control, requiring a lot of effort to do so. And now I will tell you how you can achieve the desired level of control in a complex system. A complex system typically has a lot of undiscovered issues, which can be seen like holes in a Swiss cheese. And we need to cut the cheese to test the system to detect these holes so that we know about them, are able to fill them, and have a complete system that we're happy with. Some examples of undesired behavior from real life: automotive industry, autopilot function in cars has caused cars to run into and jump over roundabouts, which is obviously not an intended behavior, right? This should have been detected, it should have been mitigated. Another example from the same function, this issue with phantom braking. A car could suddenly stop in the middle of the road, believing there's an obstacle when there's really not. That could cause serious accidents, and the driver behind you could definitely look like this. In for a real surprise, we don't want this. A personal example of good practice is me paragliding. Here you see me getting ready to be winched up after a boat to test the equipment, to get familiar with its capabilities, its limitations, to avoid dangerous situations in the future. So what we do is to try different inputs to the system and look at the behavior, see what kind of input will cause the wing to stall, spin, collapse, so that we know where these limits are and how to look for them and mitigate. The phenomenon that I'm researching is called emergence. This is often illustrated through a flock of birds. This dynamic behavior you can only explain by looking at the whole, not the individual parts, and that is really emergence in a nutshell. So it is interaction effects, synergy effects. And this term first came to with this famous Greek philosopher Aristotle, who said something like, the whole is more than the sum of its parts. And that is really the essence of emergence. And this has many aspects to it. The behavior can be positive, it can be negative, it can be expected, it can be non-expected. And here you see a guy who's obviously run into an unexpected negative thing. And we don't want our customers to look like this, right? So we want to avoid this situation. Another side to this is that it can be intuitive and non-intuitive behavior. Like, we don't want machines taking over the world. So how do we prevent that? We have to test sufficiently, have a good test strategy to detect all these things that could go wrong. And a complex system typically has a lot of parameters with huge value ranges. There's an infinite amount of combinations to test. So what should we test to know it all, know the necessary stuff? I believe that there are tools that we can use to achieve this. And one such tool is called orthogonal arrays. It's a mathematical statistical tool that will extract the relevant number of tests with the most important combinations of parameters and their values, so that you really get all the information that you need. And what I do is I look at the entire system piece by piece, one area at a time, one function at a time, and iteratively explore that area, sort of sniffing out problematic areas, exploring them. So a start could be a random place or a place based on expert knowledge where we think there might be an issue, test and move around until we find something, and then dive into that to more thoroughly explore that area, so that we really get to know the problems, how big they are, and what the shape they have, how much of the parameter space they cover. I've done this in a case study looking at autonomous surface vehicle on a search and rescue mission to detect another vessel in distress under different environmental conditions. So there's obviously a lot of parameters in this scenario. So which ones do we need to test? Here's a bunch of the parameters I've looked at, and use this mathematical key that I mentioned, set up this orthogonal array with only a few tests really, run the tests, look at the results, see if there's any interesting results, and then dive further into those. And the goal is really to sort of create a map with the system boundary. Where does the system perform according to the acceptance criteria or not? And this boundary is not intuitive. You have to test a lot to know this contour, which parameters you can combine in what way. And also within this boundary, there might be pain points where the system is not working when it should. And on top of that, I also want a sort of a contour map, seeing how well it behaves, how much margin do we have. So this is the ultimate goal that we then can use for mitigation efforts. Because a system is never stronger than its weakest link, eventually customers will use it in a way triggering undesired behavior that we have not discovered, which could ruin the product's reputation, our company reputation, and we don't want that. Just a little more testing and we can avoid that. Coming back to the elephant, how do we eat an elephant, test a complex system? Well, we work our way systematically from one end to the other, picking out the most important pieces, the pieces with the best meat, the most information, and then we're really able to cope with this big challenge.